For this problem, we're going to look at this kind of complicated function. F of x is equal to x minus 3 times x minus 4 times e to the x minus 4. And it's given that it has this very unusual property that the nth derivative of 4 is equal to n squared for all non-negative integers n. Use this property to find the Taylor series expansion about x equals 4 and determine the interval of convergence. Okay, so the Taylor series expansion is going to be summation n equals 0 to infinity of the nth derivative at 4 divided by n factorial times x minus 4 to the n. That's the Taylor series expansion about x equals 4. And we are given that this numerator here is equal to n squared. So summation n equals 0 to infinity of n squared over n factorial x minus 4 to the n. And I could simplify, but that's good enough. So that is the Taylor series about x equals 4. So up to here, that is the solution. So use this property to find the Taylor series expansion about x equals 4. That's it. Now, the second part of the problem is to find the interval of convergence. To find the interval of convergence, we use the ratio test. Okay, and so let's see, limit as n goes to infinity of, on top, I would have n plus 1 squared over n plus 1 factorial, x minus 4 to the n plus 1, all over n squared over n factorial, x minus 4 to the n. And I want the absolute value of the whole thing. So I want to find this limit, and then I want to figure out where this limit is less than 1. So limit as n goes to infinity of, okay, so let's take the pieces. N plus 1 squared over n squared. So I've got n plus 1 over n squared. Then with the factorials, I would have n factorial over n plus 1 factorial. And then here, x minus 4 to the n plus 1 over x minus 4 to the n would cancel to give me x minus 4 to the first. Okay, so let's take these one by a time. First off, I can this part's going to be 1. So the limit as n goes to infinity of n plus 1 over n. That's a rational function. The exponents are the same. So divide the leading coefficients. 1 over 1 is 1. So 1 times limit as n goes to infinity. All right, n plus 1 factorial is equal to n plus 1 times n factorial. Then I have an extra n factorial on top, x minus 4. So this is equal to the limit as n goes to infinity. N factorials cancel, and I end up with absolute value of x minus 4 over n plus 1. And no matter what x is, the denominator blows up, and so this is equal to 0. So most importantly, this limit is always less than 1. It is equal to 0. And so therefore, the series converges absolutely for all x, for all real x. And so because we've determined that this limit is always less than 1, no matter what the value of x is. Okay, so that's the solution of the problem. Now, before I stop the video, and feel free to stop the video here because I've solved it. If you're looking for a challenge and you'd like to think about to just get some extra practice with series, you may want to think about how in the world do I know that the 10th derivative of this function is guaranteed to be equal to 100? I mean, just finding the second derivative of this is going to be painful using the product rule. So finding the first derivative is going to be tough. Finding the second derivative is going to be really complicated. And somehow the second derivative is equal to 2 squared equals 4. And the 10th derivative looks almost impossible to figure out for this. And somehow if I plug in 4, that equals 100. All right, so Let me give you a hint on this, and if you'd like to ask me more about it, feel free to ask. But the hint is we can let n squared be equal to n times n minus 1 plus n. And then if I make that substitution here and then work with the factorial, I am able to work with this series and end up with this product here without directly differentiating the function f. If you'd like some practice with this, if you'd like to try it out, and if you get stuck, feel free to ask me in my office hours. But that's how I was able to construct this function that has this kind of unusual property. Again, that is not necessary. So what I have here in pink, that is not fair game for the test. That's kind of hard. What is fair game for the test is what's in blue and what's in green.